And caching has been developed to exploit temporal locality by storing recently accessed data in automatically managed fast memory. And this is a paper probably some of you have read, Maurice Wilkes' fundamental paper that introduced the term caches. Well, not the term caches, but the idea of caching. And I'd recommend you to read that. And they also exploit spatial locality, but Maurice Wilkes actually, when he introduced the caches at the time, he did not think of spatial locality, he thought about some temporal locality. It was IBM in 36085 that implemented first a cache that actually exploits spatial locality. Basically that's a cache with 64-byte blocks. And this is a beautiful paper that talks about that, about System 360 Model 85. But basically the idea is to store addresses adjacent to the recently accessed one in automatically managed fast memory. So I'm going this relatively quickly because we've already covered caches, but this is going to be fundamental in all parts of the design. And I've told you before in one of these lectures that the cache needs to be tightly integrated into the pipeline. Ideally, you want the access in one cycle so that dependent operations do not stall. And if you have a high frequency pipeline, you cannot make this cache large, but you want the cache large. You want a large cache and a pipeline design to actually get more capacity, right? As a result, we have cache hierarchies today. So you have level 2 cache, level 3 cache, ... Just one other thing that we may get to at some point is, do you manually or automatically manage the cache, right? If you manually do, then programmer manages data movement across levels. This is usually too painful for the programmers on substantial programs. Maybe not as much for the systems programmer, but this is still done in embedded processors today with on-chip scratchpad memories, right? In lieu of automatically managed caches. When you say cache, it's usually automatically managed. It could use software hints to do better. And when we talk about tiered latency DRAM, basically we'll introduce a caching area in DRAM that could be managed by the programmer too. Automatic means hardware manages data movement across levels transparently to the programmer. Programmer's life is much easier, right? The programmer doesn't need to worry about things. And simple heuristic, keep most recently used items in the cache. We've seen that that doesn't work very well in multi-core, right? When we talked about caches. The average programmer doesn't need to know about it when you manage it this way, but if you really want to optimize your programs, perhaps you would like to know about it. And I think I'll skip this one, but this is the paper that I would recommend again. So basically, we're going to cover, this is the memory hierarchy, and we're going to cover, focus mainly on this part, main memory. Although some of the ideas may be applicable to very large embedded DRAM caches, as well as very large SRAM caches too. Okay, let's go into the DRAM subsystem. This is the top-down view of the DRAM subsystem organization. Basically, you start with a channel and you can have multiple parallel channels. And channel consists of DIMMs, and a DIMM consists of multiple ranks, and a rank consists of multiple chips, which consists of multiple banks, which consists of that two-dimensional structure. So it's an, I think, n-dimensional structure if you actually look at it this way. This is my bad drawing, but this is basically the what a DRAM bank looks like. You have this row address latch and you have this column address latch. And we're going to take this bank and actually build up something from it. I've already covered some of this, but if you want to access a closed row, you want to activate, to open the row, you want to read write. This command operates on the row buffer, which is this part. And you want to pre-charge the command to prepare the array for the next access. And I'm going to skip this because we've already talked about this. Let's see how fast PowerPoint can go without crashing. Okay. Okay, well, it did go pretty fast. So a DRAM chip consists of some number of these banks. It's 8 today in DDR3, but there's nothing fundamental about 8 except for all companies agreeing on what they can manufacture, right? That's or what they can reasonably manufacture. And banks share today's DRAM. Banks share command, address, and data buses because they consume pins, right? You want to minimize those pins. And the chip itself has a very narrow interface. Again, the limiter is the pins, number of pins you have. Basically, you can have 4 bits or 16 bits. And this is what a chip looks like. This is a 128 megabytes, M times 8 bits. So it's a 1 gigabit chip, right? Basically, the output is 8 bits, and everything I told you here exists. This is the bank that you can see. This is the bank 0 row address latch and the decoder. And this is the sense amplifiers over here. And this is the column decoder that takes the sense amplifiers and decodes it. And this is the column address latch. And this is the row address latch. And you can have refresh inside here. When the DRAM bank is refreshing itself with a command from the memory controller, it refreshes itself from here. And you have a bunch of control logic. And this is the address registers coming, specifying the bank and specifying the row or column. And remember that those were multiplexed. And there's a bunch of termination logic that ensures stabilization of the chip. And that actually consumes a lot of the area. So DRAM rank and module, basically a rank is when you can have multiple chips that are operated together to form a very wide interface. The goal is to get a wide interface, and you get it through a rank. All chips comprising the rank are controlled at the same time. They respond to a single command. And they share the address and command buses, but provide different data. Basically, this is like a rank of soldiers. You say, I guess left foot, they all provide you their left foot, except they're different left foots, right? Left feet, right? So that's the analogy. Basically, a DRAM module consists of one or more ranks. One example is the dual inline memory module, and this is what you plug into your motherboard. If you have chips with an 8-bit interface, for example, to read 8 bytes in a single access, you put together 8 of these chips in a DIMM. So in a rank, you have 8 chips, basically. And this is what it looks like. Basically, this is one rank of a DIMM, dual inline memory module, and you have 1, 2, 3, 4, 5, 6, 7, 8 DRAM chips that are operated together. This is the rank. And this is one other way of looking at it, basically. This is from one of the papers. So advantage of a rank is now it acts like a high-capacity DRAM chip with a wide interface, right? It's flexible. Memory controller doesn't need to deal with individual chips. From the memory controller's point of view, it's flexible. Because the memory controller doesn't want to get bit by bit, perhaps. Maybe it wants to get a single cache line at a time. And actually, that's what happens in today's systems. You get 8 bytes, and then you burst out the remaining I guess 56 bytes. DRAM has burst mode where it can provide the remaining bytes quickly. Disadvantages, now your granularity of access cannot be smaller than the interface width. And this could be an issue, right? Because if your granularity is 64 bytes, then you're always getting 64 bytes even if you need 1 bit from DRAM. And that could be an issue going forward. I will not talk about that in detail, but the granularity of transfer within DRAM and across parts of DRAM is an interesting issue to examine. There have been several papers, several from Matan Erez's group from UT Austin actually is, that's an interesting. They've examined how you can make this granularity dynamic. But there are also other issues of granularity. For example, here we've assumed that you actually bring down a lot of data at the same time, right? But that's high power consumption if you're not going to use all of that data. And people have looked at that problem. But there are low-cost solutions to reduce the amount of data that you bring in on an access don't exist today. And looking at how to do that at low cost is an interesting research problem. It's a tough research problem. You can actually have multiple DIMMs and interconnect them in some way. This is not the greatest picture in the world, but you have a single DRAM controller, and it's interconnected in a mesh topology. If you actually follow the arrows, you will perhaps figure out that this is mesh. I wasn't able to, but you may be able to. But basically, you can have some kind of interconnect and address these different DIMMs, right? This enables even higher capacity. Today, this is how you get capacity, right, in DRAM. Apart from technology scaling. The disadvantage is your interconnect complexity and energy consumption becomes very high, and your wires can become non-scalable, right? That's because these are actually wires in your motherboard, and they're expensive. They're more expensive than what you have on your chip. So DRAM channels, so we've covered ranks, DIMMs. Actually, a DIMM can have multiple ranks, and we'll see that when we go through the top-down view. Channel is basically, you can have multiple of these, right? You can have one channel controlling a bunch of DIMMs, and you can replicate this and have another channel doing the same thing, have another channel doing the same thing. And now you can connect all of them to your multi-core processor. Of course, now you need pins for different channels, right? So having more channels actually increases the cost of your system. So you can have independent or dependent channels. Independent channels means you basically have two separate memory controllers that can do different things. If the channels are dependent or lockstep, this is essentially very similar to rank, right? You have a single memory controller giving the same commands to those channels and getting more data. So today, what is really favored is the independent channels, although there are many companies like IBM and their Power 7, they have a lot of dependent channels also. Okay, so generalized memory structure, basically you have a memory controller that controls a channel which consists of multiple DIMMs, which may consist of multiple ranks within themselves. And within each DIMM, you have these chips where you have banks, in this case 4 banks, and you have a two-dimensional structure, columns and rows, and a cache line basically resides within a row and across different columns, in this case 4 columns, for example. So this is probably the 5-dimensional structure. And this is another way of looking at it. Let's take a look at it from the top down with a real example. Basically, this is what we started with, the DRAM subsystem. With a real example, basically a channel looks like this. And the Halem processor may have 2 channels. And a channel consists of multiple DIMMs. If you look at a DIMM, you have the front of DIMM and the back of DIMM. And you can have ranks on both sides. Basically, rank is a collection of 8 chips in this case. And if you have error correcting codes, usually people add 1 more chip over here just for error correction, and that's your overhead for error correction. At least the space overhead for error correction. There's a lot of other overheads for error correction too. So what does a rank look like? Let's say you have rank 0 and rank 1. If we expand that, basically these ranks share the address and command buses as well as the data bus. And you can think of it as a mux. You mux out data. You have a switching penalty between the ranks because of this mux, because it takes time to actually stabilize those I/O circuitry. If you break down a rank, this rank looks like this. Basically, you have multiple chips that provide different parts of the data that you're going to read. 64 bits, every rank provides 8 bits over here. Every chip provides 8 bits here. If you break down a chip, now it looks like 8 banks, and I don't think it's... So it looks like this one has a different problem. And the problem is, you can see the silhouette of those, right? Basically, those are banks. At some point, we'll get a projector that has a good color scheme. But basically, imagine that there are banks here. And what does a bank look like? The bank looks like this, as we've seen before. And we've already seen this before, so I'm not going to go into this in detail. So how do you actually transfer a cache block? Let's take a look at that quickly, because this will be useful later on when we actually talk about the bulk data transfer. It's going to be very inefficient to do bulk data transfer cache block by cache block. So let's say this is your physical memory space and this is your 64-byte cache block. This is mapped to DIMM 0, rank 0. And within that, it's mapped this way, basically. Because each rank provides pieces of the cache block, basically this is row 0, column 0. And another chip maps the next 8 bits. Another chip maps the next 8 bits, ... And basically, this is how we get an 8-byte cache, 8 bytes of the cache block. The next 8 bytes is in row 0, column 1. The next 8 bytes is in row 0, column 2, right? ... Basically, a 64-byte cache block takes 8 cycles, 8 bus cycles to transfer. During the process, 8 columns are read sequentially. I think that's okay. Basically, what are the latency components to actually transfer this? First, CPU needs to request the data. So there's some transfer time from the CPU to the controller on chip. There's controller latency, there's queuing and scheduling delay, and the controller converts the request to basic commands, activate, read, write, pre-charge, and a bunch of other commands. And we will see some of that. And then controller transfers those commands to the DRAM, and there's DRAM bank latency, which is perhaps the dominant latency. And this could be row hit. CAS means column address strobe. If the row is open, basically just send the column address. RAS means row address strobe. If the array is precharged, if the row buffer is closed, you send row address strobe and column address strobe. In the worst case, you send a precharge, row address strobe, and column address strobe. And that's the most costly access. Now I'm assuming you're on a single chip here, right? If you have multiple chips, then this is again just multi-core, a single chip. And after the data is transferred, there's DRAM to CPU transfer time through the controller. I had a newer version of the slide, but apparently it got lost here. But that actually takes time also. You need to transfer the data back to the memory controller, and the memory controller needs to transfer the data back to the cache and the core. Okay, so multiple banks and channels, what is the benefit of it? This enables concurrent DRAM accesses. And bits and address determine which bank and address resides in. That's why this mapping is very important. Multiple independent channels serve the same purpose, but they're even better because they have separate data buses, right? If you have independent channels, they're totally separate. And enabling more concurrency in DRAM, which is needed as you go into multi-core or larger scale multi-core, requires reducing the bank conflicts as well as channel conflicts. And again, there are many different techniques to do that. This is not a new problem. People have explored this in parallel processing, especially vector machines. You have lots of data parallelism, right? And you're operating on huge arrays. And how do you map these arrays to different banks such that you maximize your bandwidth? Because in many cases, your processor is bandwidth limited. It's like a GPU again. GPU is a vector processor or array processor today. So people have looked at this problem. How do you actually do this? And there are many ways. I'll briefly talk about some of these. One could be selecting and randomizing the bank and channel indices in the address. Basically, lower order bits have more entropy, and maybe you use those to determine what is the bank address, right? Or you can use randomizing hash functions. So you can take the address and I think actually I might have something over there later on. But you can take the address, let's say this is your address, and take some bits of it and go through a hash function to determine the bank address, right? And people have proposed things like this. One seminal paper in this area is Bob Rao's pseudo-randomly interleaved memory. And I would recommend that paper. It's very heavy on math, but it discusses a lot of issues related to how to do this mapping. I think it was in NISCA 1991. But basically, people have looked at randomizing mapping such that you maximize the performance. So we're going to assume all of that. Assuming all of that, you still get bank conflicts. That's interesting because it just happens, right? This is similar to birthday paradox, for example, right? Where people actually, you don't need that many people to share a birthday in a single room to, because even though you have 365 days, you only need, I think, 23 people or so to get to maximize the probability of sharing a birthday. Anyway, that's something to read. You know about the birthday paradox, right? That's okay. So how multiple banks and channels can help? I'll get back to that actually in bank conflicts. I have another story related to bank conflicts. You see this in real life also, right? You always get these bank conflicts. Even if there are so many desks here, maybe desks is not a good thing. I see this when I go to a gym, for example. In the United States, you have lockers in the gyms. And you usually end up very close to someone else, even if the gym is empty, right? That's interesting. That's what I find all the time. You have lockers all over the place, but somehow the things work out such that the lockers that are close by is always used. Okay, I think I'll skip this one, but this is basically showing that you can overlap the latency. If you do not have banks, you need to have serial access. If you have banks, you can pipeline the accesses. The advantage of multiple channels is you can increase the bandwidth. So one question is, why don't we have more channels? That scales the system really well, right? This increases the bandwidth and it enables multiple concurrent accesses if they're independent. But there's a big disadvantage, which is it's much higher cost. It has more board wires, more pins, and that makes it difficult to scale the system. And address mapping is another question that we will not tackle right now, but we will cover in the third lecture a little bit. Basically, in a single channel system, this is assuming a single channel, but one way of mapping the data, you can interleave the rows. You can interleave physical memory at the row granularity. Let's say consecutive rows of memory could be in consecutive banks. Right? It could be in consecutive channels too, right? But in this case, we're assuming a single channel system. Basically, here, I think, how big is a row in this case? I guess a column is 11 bits, which means that the row is 2 kilobytes, right? So 2 kilobyte of physical memory here is in this bank, the next 2 kilobytes here, the next 2 kilobytes here, the next 2 kilobytes here. Now you can imagine that this is nice for streaming accesses, right? Because you can stream through one bank very quickly. On the other hand, a lot of systems actually employ this, which is cache block interleaving. Consecutive cache block addresses are in consecutive banks. Now what you can do is you can actually access consecutive cache blocks from different banks. You can maximize that parallelism. And you can think about a lot of different things. But this is one example, bank mapping randomization some processors employ. I think this is employed in some Spark processors and some other processors also. Basically, DRAM controller can randomize the address mapping to banks such that bank conflicts are less likely. Basically, you take some bits from here and some other bits from here, XOR them, and you form a bank index. This is actually a general technique to reduce conflicts whenever you map data to a location, right? And this paper actually covers it in a more detailed way. This paper talks about different arrays that you can use to do the hashing function. So with multiple channels, address mapping becomes even more complex, right? Where do you put the channel bit is one question. And where are consecutive cache blocks in this case? But I'll let you figure that out. And you can actually get even more fancy, right? You can actually divide the column bits. You can take the bank bits from some other place, right? Over here. So yeah, many different choices here. And this all affects the bank conflicts you get. This all affects the interference between applications you get also. Maybe you want to be able to control this, right? And the question is, how can you control it? Today, there is no direct way. So this is going to be similar to the page coloring that we discussed in caching. Basically, the operating system can influence where address maps in DRAM, right? So if you look at this virtual address, this gets translated to the physical address. And you can see the physical address as it's decomposed to different structures in DRAM, right? Basically, if you look at this, bank bits come from, are influenced by this virtual to physical address translation, because physical address, the bits that are taken from physical address for the bank come from this virtual page number, right? This translation. Basically, what the operating system can do, if it knows that these bank bits can come are coming from these 3 bits, the operating system can color the banks, right? The banks can have different colors, and maybe the operating system can allocate different colors to different applications. This way, different applications can map to different banks. This is the page coloring that we've seen earlier, except at the memory level. That way, you can reduce memory interference. One big problem today is this structure is really not known. It's not exposed to the operating system. Let alone the operating system, it's not even exposed to the processor designer. So actually, the memory controller has this, but it's not exposed anywhere. You can figure it out. You can actually, if you're interested in this, a very good assignment is to reverse engineer this mapping. And you can write programs to reverse engineer this mapping. And it's doable. I've had several students do it. And it's a lot of fun to do it. And you'll be... it's not as easy as you think, because there's a lot of randomization that happens, and you'll need to figure out which bits are XORed with which other bits to randomize the address. But the bottom line is basically operating system can control which bank channel rank a virtual page is mapped to, but it's costly because it's not exposed. So one solution going forward, this is also what I mean by system DRAM co-design, is to expose the structure much better to the higher level such that system can take advantage of it to solve different kinds of problems. And if it's exposed, the operating system can perform page coloring to minimize bank conflicts or minimize inter-application interference. And we'll cover some solution later on at the channel level. Okay, I think a few more slides just to talk about how these things work. DRAM refresh, I've talked about this. DRAM capacitor charge leaks over time. And the memory controller needs to read each row periodically to refresh the charge. Basically, what does that mean? Reading each row periodically. You activate the row and pre-charge the row every n milliseconds. Today's n is 64 milliseconds. Basically, every 64 milliseconds, you're reading every single row, which is very costly. And if the temperature is high, if it's 85 degrees Celsius, this goes down to 32 milliseconds. There are many implications on performance. The DRAM bank is unavailable while refreshed. There are long pause times. If we refresh all rows in burst, every 64 milliseconds, the DRAM will be unavailable until refresh ends, right? And that's a bad idea. So because of that, this is called burst refresh. All rows are refreshed immediately after one another. But today, many systems employ distributed refresh, where each row is refreshed at a different time at regular intervals. And this is one example from one of Micron's data sheets. Basically, burst refresh looks like this. And if you actually have enough row, if you actually have not a lot of memory, you have these idle times where you're not refreshing. Actually, these are the idle times, actually. This is when you're actually refreshing and memory is not accessible, and this is when the memory is accessible. But many of today's systems actually interleave these refreshes of different rows, such that you get better quality of service impact. So distributed refresh eliminates long pause times, but it doesn't get rid of refreshes. So we'll take a look at some approaches to get rid of refreshes later on. Can we actually reduce the number of refreshes? And that's an important direction going forward, I think. I'll give you some ideas that we've been looking at. So there are many downsides of refresh. This is just to prepare you for later. Energy consumption. Each refresh actually consumes energy. And I already told you this. And refresh rate limits DRAM density scaling. As we go forward, refresh will become a bigger problem because refresh rate will increase, and also as we increase the capacity, the number of refreshes will increase. As a result, you get this exponential curve on the impact of refresh on latency as latency as well as energy. Oh, okay, this was my fault. This was the user error versus PowerPoint error. Normally, actually, people have done a lot of reliability studies, right? You've probably taken dependable systems courses from our professor here. But people have done a lot of reliability studies, and user errors in at least large-scale systems are the biggest cause of unreliability if you have operators. Now, with Microsoft products running on Apple, I'm not sure if it's the user error that's more common or the product error that's more common. Okay, DRAM versus other types of memories. I think basically I'll talk a little bit about the memory controllers because we're going to cover that in quality of service. But long latency memories have similar characteristics that need to be controlled. The following discussion will use DRAM as an example, but many of the issues are similar in the design of controllers for memories. So flash controllers that can be actually similar to DRAM controllers at a different level, right? And emerging memory technologies will need to have controllers also. So the controllers that I will describe will be specific to DRAM, but other technologies will have similar characteristics. And I didn't talk about spin transfer torque magnetic memory, but maybe I'll talk about it tomorrow, because this is another memory technology that's very promising. And arguably, some people would argue that this is more promising today than phase change memory. And actually, there's another memory that's RAM here that's not on these slides. So what are the functions of a controller? Whenever you design a DRAM controller, you need to ensure correct operation. That's number one, right? Refresh and timing. Second, you need to service DRAM requests while obeying the timing constraints, while ensuring the correct operation. And there are many constraints: resource conflicts, bank, bus, channel conflicts. There are minimum write-to-read delays. You cannot issue a read after, so many cycles after you issue a write, because the bus needs to stabilize. The DRAM controller needs to translate requests to DRAM command sequences. The third function, the controller needs to buffer and schedule requests to improve performance. And this consists of row buffer management, bank management, rank management, bus management, and reordering of requests. If you do first come, first serve, it's very simple, but it's not the highest performance. So you would like to take advantage of the row buffer, you'd like to take advantage of other characteristics. And we will see that this becomes much more complicated in multi-core. And the fourth thing that's very important today is managing power consumption and potentially thermals in DRAM. How do you turn on and off DRAM chips, manage power modes, minimize energy, basically. One issue, this is actually probably an old issue, where do you place the DRAM controller? Traditionally, it's been in chipset, basically separate from the processor. But as we've discussed when we talked about multi-core, the core actually consumes a lot of the system components, and that's today, many of the DRAM controllers are on the CPU chip. But if you give up something by putting the DRAM controller on the CPU chip. Basically, in the chipset, you get more flexibility to plug different DRAM types into the system, right? Because you can basically keep the interface to the DRAM controller and the chip the same, but you can have different DRAM controllers there. Whereas here, if you put it on the CPU chip, it becomes more expensive to support more DRAM controllers. You cannot support DDR3, DDR2, DDR4, DDR5 at the same time, or FBDIMM, for example. In chipset, you have less power density than in the CPU chip also, right? Whereas CPU chip is a very active part of the system. But if you put it on the CPU chip, you get reduced latency for main memory access, which is a big advantage. And when AMD put their memory controllers on chip, they saw a latency cut of 1/3 in the main memory. And I think that pushed Intel to put their memory controllers on chip, because there were a lot of discussions in Intel, and people didn't want to put the memory controller on the chip, I believe, because they were late in doing this for a long time. But eventually they did it, because that latency reduction is actually very important. But then you lose flexibility, right? Actually, I believe one of the reasons was Intel wanted to support different interfaces, right? There was FP fully buffered DIMM at the time. That was a different interface than the SDRAM interface. And as a result, if you want to keep flexibility, it's going to be tough to put it on chip. And the other upside of putting the DRAM controller on chip is you have a higher bandwidth between cores and the controller. Now you can have more information communicated. For example, the core can say this request is more important. Whereas otherwise you need to consume pins to go through to go off chip. Okay, so what does a DRAM controller look like? Basically, these are CPUs, and I/O actually shares the DRAM controller also, assuming you're doing memory mapped I/O or DMAs. And you have an arbiter, and you have some request queues for different banks. It could be monolithic again. And there's address translation between the arbiter to figure out which bank a request goes to, and there's command scheduling from here. And there's a signaling interface here, which we will not deal with. We'll mainly deal with the design over here, especially in the third lecture. And this is another way of looking at it. Yeah, basically different bank request buffers coming from L2 caches. The requests go into different bank request buffers, and you can have schedulers for different banks that pick a request, and later the DRAM bus scheduler can pick one of those requests to schedule onto the bus. We've already covered some of these scheduling policies. But basically, first come, first serve, row hit first, oldest first. I won't talk about it again, but the goal is to maximize row buffer hit rate. But scheduling is actually done at the command level in many controllers today. You could do it at the request level also, but you could do it at the command level. Basically, you translate all these requests into commands, and the controller says, this request needs this command to be serviced. And then column commands are prioritized over row commands. Read write is prioritized over activate precharge. This is basically row hit first policy. And within each group, older commands are prioritized over younger ones. So this is actually a very open area also that we've been looking at for a long time. A scheduling policy is essentially a prioritization order, right? And this prioritization can be based on many things. It could be based on request age, row buffer hit miss status, request type, prefetch, read write, requester type, is it a load or is it a store? How important is the request is it the oldest miss in the core, or is it one of the younger ones? Or how many instructions are in the core are dependent on it? Or is it making many threads wait? So you could actually expose all of these to the memory controller to maximize performance. And it becomes tough to actually design the memory controller. There's also another policy, which is the row buffer management policy. How long do you keep the row buffer open, right? Open row policy says keep the row open after an access. If there's another access that's coming to that row, this is a good idea, probably, right? If there's not, then you get a row hit. Otherwise, if the next access might needs a different row, then you wasted time. You could have pre-charged the row, and you could have saved some time. So closed row policy tries to get the best over here. Basically, close the row after an access. Of course, if there could be a very strict closed row policy that closed the row right after the access without looking at the request queue. So many controllers actually today, if no other requests are already in the request buffer that need the same row, then they close it. So they actually scan the request buffer. Only then they close it. So it's an intelligent closed row policy. The upside is next access might need a different row. In this case, this avoids a row conflict, right? You basically do the pre-charge preemptively or proactively. But if the next access might needs the same row, then you've done the wrong thing with the closed row policy, right? So this leads to an extra activate latency. So this actually affects things a lot, because you're basically an extra activate doubles the access time, right? So there are adaptive policies that people have implemented in real designs, but I think this is also an interesting research area going forward. Predict whether or not the next access to the bank will be to the same row. I think that's interesting. And you could actually use some system level information, perhaps from the program, to do this prediction. I do not know of any very comprehensive work that actually looks at this. So if you're interested in that, this could be an interesting area, I think. So I'm going to skip this, but this basically tells the same thing. So why are DRAM controllers difficult to design? You've seen already that there are many things that they need to do. They need to obey the DRAM timing constraints for correctness. So what does this mean? So there are actually many timing constraints in DRAM. There are more than 50 in one of the data sheets. One is WTR, for example. This is the minimum number of cycles to wait before issuing a read command after a write command is issued. This is the raw cycle time. This is the main latency component of DRAM today. Minimum number of cycles between the issuing of 2 consecutive activate commands to the same bank. And there are a bunch of these. The second is they need to keep track of many resources to prevent conflicts, right? All of these dimensions they need to keep track of so that they need to handle DRAM refresh at the same time. And they need to optimize for performance at the same time too, in the presence of all of these constraints. And reordering is not simple, because if you want to figure out which request hits in the row buffer, it's actually a content addressable search. You could make it simpler, but it's still a content addressable search. You need to search the content sometime. And if you want to predict the future, then it becomes even more difficult to design. And some of these DRAM constraints are here. As you see, there's read to precharge. And this is only some of them again. And you can read this paper that talks about this. We can talk about that paper some of the time. So if you want, I'll get to some work that was motivated by this. But if you want more information on DRAM operation and constraints, these 2 papers that I've already assigned are very good resources. Actually, these 2 papers describe with figures what exactly are these constraints. And some of them describe why they're there also. So why are these constraints there? Just briefly. You don't have to have all these constraints, right? You can just say every access takes some number of nanoseconds, and that number of nanoseconds is just fixed, right? The problem with that is that needs to be the worst case access time. And that worst case access time is much worse than the best case access time. That's why we have these different latencies in DRAM today. So, because it's a very latency sensitive component and we want to get the best out of it. That's why we have all these different constraints. But this makes the DRAM controller designer's job much harder. And if you ever designed a DRAM controller, probably you know what I'm talking about. So we've actually looked at trying to make this easier a little bit. The idea is, I'll take a break right after describing this idea. Basically, because DRAM controllers are difficult to design, it's difficult for human designers to design a policy that can adapt itself well to different workloads and different system conditions. So the question we started out with was, can we design a memory controller that can optimize its policy dynamically without human designer dictating the policy? If you look at the previous policies, first come, first serve, human designer dictates the policy. First ready, first come, first serve. The goal is to maximize row buffer hit rate. And the human designer again dictates the policy, right? And the policy doesn't change over time. Our idea was to design a memory controller that adapts its scheduling policy decisions to the workload behavior and system conditions using machine learning. And observation was simple. Basically, reinforcement learning method maps nicely to memory control. And I'll show you an example. Basically, we treated the memory controller as a reinforcement learning agent that dynamically and continuously learns and employs the best scheduling policy. I will not go into detail because there's a lot to cover in reinforcement learning here. I'll point you to the paper. But this is actually a very promising direction going forward, I think. Basically, if you look at reinforcement learning, what happens is you have an agent that interacts with the environment. And agent basically is in some state. And at that state, it takes an action. And that action creates a reward to that agent. And based on this reward, the agent can update the value, this is called the Q values in reinforcement learning or Q learning, value of a state, of taking an action at a state. Basically, you have these state, at a given state, you have potential state action pairs, and you can figure out the action that will maximize the reward in the long term. That's the idea. Basically, you have a table that maps state action pairs to long-term rewards. And whenever you're in a particular state, you index that table and you pick the action that would maximize the long-term reward. And immediately you get a reward and you use that to update what kind of reward you will get in the long term. So you actually weight the reward based on the long term. And that's the idea. So this is very much similar to the memory scheduler here, assuming you're optimizing for memory bandwidth. So a scheduler is the agent. environment is the system, and scheduler takes an action, which is the command it chooses. And you can choose from many different commands. It can actually choose from refresh also, right? Although there's some elasticity in refresh, actually. You can delay refreshes for a short time. But beyond some point, you don't want to delay refreshes. But basically, you choose the command, and the scheduler observes the data bus utilization. And based on that, updates the current state. And how does it encode the state? Basically, we've looked at many different possible state encoding. I think hundreds of different system parameters. And we've selected features that seem to be the best for these state attributes. Some of them, for example, how many reads do you have in your scheduling queue? How many writes do you have in your scheduling queue? How many of them are the oldest requests in the buffer? So we've actually, not exhaustively, but did some rigorous study to extract the features that were interesting. And if you design a memory controller like that, then basically a memory controller observes the state in the transaction queue and looks up this table that says, for this state, choose this action, because that will maximize your long-term reward. And you'll get a reward and update the values. And that's the idea, basically. You have a reinforcement learning agent acting as a scheduler. And I think this is basically another way of looking at it. You have this transaction queue. Scheduler takes the state parameters, state attributes from the transaction queue, and then chooses the action that would hopefully maximize the reward. I don't show this table over here, but the paper does. And I'd encourage you to read the paper if you're interested. I think going forward, designing systems that use machine learning in this way would be much more interesting, because the systems are becoming much more complex going forward. And memory control is a nice place where this fits, because the memory controller can be actually, what memory controller does can be abstracted as a Markov decision process, it turns out, assuming data bus utilization is your target. And that's what you need to map this problem to reinforcement learning. But some other problems don't map very nicely, I think, like caching. Not to reinforcement learning, actually. You don't get this nice reinforcement loop, at least not on a per request basis. Okay, so what is the performance of this? So you can read the paper that tells you how to implement it in a reasonable way also. I don't believe the implementation is that bad, but you still need this table. That's a little bit expensive. I think there are two impediments to implementation. It's always good to think about implementation. One is the hardware cost. The other is the comfort of the designer. Here, whenever I talk to designers about this, the designers are not necessarily comfortable because it's a black box, right? With the row hit first scheduling policy, they know that how it's going to work. Whereas with this, it's a black box, and they haven't decided. Even though there is high-level theoretical intuition, there is no immediate intuition that the designer gets. It's not a row hit or row miss. Okay, what are the performance results? So if you look at this, these are parallel applications over here. And this is the in-order, first-come, first-served scheduling policy. That actually performs pretty badly. This is the row hit first scheduling policy, which performs more than 40% better than in-order, first-come, first-served. And this is reinforcement learning-based scheduling. You get about 20% better performance on these parallel applications by maximizing data bus utilization. And this is the best you can do, optimistic policy. Basically, you eliminate all timing constraints except for the data bus conflicts. That's actually a very optimistic policy. Not policy, it's an unimplementable and still very optimistic policy, upper bound. And this is what happens actually if you increase the number of channels. So reinforcement learning-based controllers still provide you good performance with more channels. And the reason is basically you schedule, if you do the scheduling in a myopic way by just looking at whether this will be a row hit, that doesn't maximize data bus utilization because there will be writes that will be coming in. So one example that I will give is current memory controllers cannot switch between reads to writes fast because there is a read to write switching penalty and write to read switching penalty. And as a result, what they do is they accumulate the writes, and writes are not critical. And once the write buffer is close to full, they switch to a mode saying, okay, now I'm going to service the writes, and the reads will be delayed. You cannot anticipate this easily if you're not looking at many different metrics, right? And reinforcement learning controller seems to anticipate this better. As a result, it's better than the row hit first scheduler. And there are many other things in DRAM like this. Okay, one last thing. DRAM chips also have power modes, and the idea people have explored is when not accessing a chip, power it down. There are a bunch of different power states like active, all banks idle, power down, and self-refresh. This is the lowest power. The only guarantee here is the DRAM chip is always refreshing itself. And state transitions incur latency. So if you want to go from power down to self-refresh, it's quick and you save a lot of power. But if you want to go back from self-refresh to power down, well, or self-refresh to active, that takes a lot of time. It's actually in the order of almost microseconds, I believe. As a result, you have an optimization problem here also, right? How do you actually decide when to power down a chip and what state to put it onto? And people have looked at this problem. If you're interested in this, I think going forward with multi-core, with memory interference, this becomes also interesting. How do you do the power management? And I think going forward, there will be hopefully more interesting and more finer grained power management in DRAM. If you look at today's DRAM, the power management is not at the bank level. It's actually at the rank level, which is a very coarse grain. If you can do it at the bank level, you can probably get better power characteristics. Okay, I feel like I've talked a lot and quickly. Any questions before you take a break? Yes?
This row buffer is kind of a cache.
Mm-hmm.
So all those speculative, predictive techniques used for cache, are we trying to adapt those, or this is a quite different game for the row buffer?
So that's a good question. So row buffer is a cache, but it's also not fully a cache because you have to access it. Meaning you cannot take any data from DRAM without putting it into the row buffer because it's also the sense amplifier. So it is a cache. Once you access it, the key question is, do you keep the data or not keep the data over there? So in that sense, it's a cache. Yeah. But if you want to access something else from the same bank, you have to destroy that row buffer. So you don't have an option of bypassing the cache, for example. But people have proposed actually adding more row buffers. Now they're different from the initial row buffer because you don't. So row buffer is really needed because it's a sense amplifier. But people have proposed cached DRAM, where you add more SRAM cells to buffer rows, and then you can manage the cache that way. And I'll talk about those a little bit when we actually we'll introduce some other way of using part of the cache as part of DRAM as cache. We'll get to that, I think. The downside of those cache DRAM techniques have been, once you add one more row buffer, it's expensive in DRAM, and it's about actually, we've done some studies where additional overhead of cached DRAM is about 50% of the DRAM chip, because this is SRAM chips.
And then
SRAM rows, sorry.
Dual row buffer implementation, are there any commercial examples of that?
Of multiple row buffers?
Dual, at least.
So that's a good question. So I believe Hitachi tried it in the 1990s, and they've actually proposed, Toshiba also. And they've looked at these multiple row buffers, but cost per bit was so dominant at that time that...
Because a bit more residence in the row buffer may result in more hits on that, but meantime, you're delaying some other things that will come into that row buffer. Of course, there's a trade-off there.
That's right.
Yeah, if you have a dual backup, then mimicking that. And
that's right.
the other
yeah.
Switch.
Yeah, I agree. And people have explored that as part of the cached DRAM. The main problem has been the cost. Maybe it needs to be re-examined, and we're examining it in a different way. I'll talk about this tiered latency DRAM. Maybe we can contrast the cached DRAM to that at that time.
Okay.
Any other questions before we take a break? Okay. Shall we take a break for 5 minutes? It's been a long lecture this time.